Hi, this is Mr. King. I'm going to go over some factoring strategies in this video lesson. Factoring out the GCF, the sum product pattern, factoring by grouping, perfect square trinomials, and the difference of squares pattern. Let's start with the greatest common factor, or GCF factoring. This is always the first kind of factor to look for, and it always, well, almost always makes it easier when we do factoring. So we always look for one because if there is one, it makes things easier often, or sometimes it is just the only thing we can factor. And in this case, we see that we've got a 3 multiplying the x squared, a 12 multiplying the x, and then we have the 36. The biggest number that divides into each of those is 3. And we see this divides into 1, this divides in 4 times, and this one divides in 12 times. And so the GCF is 3, and I write it down, and I make empty parentheses. And what goes in the first spot in the parentheses? Well, I like to say, well, what do I multiply 3 by to get a 3x squared? And it's an x squared. So I'm thinking about how I would distribute the 3 into something to get back to the 3x squared. And to get to the 12x, I would multiply by a 4x. So 3 times 4x is a 12x. And then 3 times a negative 12 would be that negative 36. That's one way to do it. Some people like to start with the trinomial, and they locate the GCF again. They figure out what that is, and it's a 3. Make the parentheses, and then we divide each term by 3. And we see that when we divide 3x squared by 3, we get x squared. Divide the 12x by 3, we get the 4x. And divide the 36 by 3, and we get that 12. And as we can see, these are the same answers, aren't they? So take your pick. Either way works. So in this next example, we've got a 6x cubed minus 15x squared minus 24x. This time, the number that's common is 3 once again. And so I'm going to write the 3 down, and we'll divide each of these one at a time in a moment. But there's the number. Now there's an x cubed and an x squared and an x. So the lowest power is part of the GCF. So 3x is the GCF this time. And when we divide each of these terms by 3x, we'll see that 6 over 3 is a 2, and x cubed over x to the first is x squared. And then 15 over 3 is 5, and then x squared over x is x. And then 24x divided by 3x is 8. And this one is factored. So again, this is the GCF here. And this is an example of a GCF that is a monomial that's a number multiplying a variable. Whereas in this example, our GCF was just the number, and it was a 3. So this next example is factoring a quadratic trinomial that has form x squared plus bx plus c. And we're going to use the sum product pattern here. And the sum product pattern comes from this. Well, there is no number multiplying x squared other than the hidden one. And this is a particularly nice type of trinomial to factor. And what I typically do is this. I say, what factors of 3, and that's of course the number c on the end in the form, what factors of 3 add up to the number in the middle, 4, the b value. And often I will teach students to make a little table where we say what factors of 3, like that, and I use the x with a circle to represent factors, and then they have to add up to the plus sign with the circle, the number in the middle, 4. Now this one is a particularly easy example. We know that 1 times 3 is 3, and that 1 plus 3 is 4. And so we see quickly that those numbers work. Now in this form, because we have x squared, and it's 1x squared plus 4x plus 3, we're going to factor this into two binomials. And the first positions are always x. The other values that come after the x's come from the 1 and the 3, the two factors that we found that work. And so we're going to put the 1 here, plus 1, and then a plus 3 here. Notice that all the numbers here were positive. Now if you want, we can check our answer by FOILing. Remember, FOIL is double distribution. And so the x's multiply to give us an x squared. And then the outer product is a 3x. The inner product is a 1x. And the last terms, 1 times 3 is 3. And this can be simplified because these are these are like terms. So we get x squared plus 4x plus 3. And we see that, in fact, it worked. So that was a check. Here's another example. Similar but different. Again, there's a hidden 1 multiplying x squared. But in this case, both numbers are negative. But again, we need two factors of a negative 4 this time, the number on the end. And these factors need to add up to the number in the middle, which is the negative 3. So here's the sum, if you will, and here's the product in the sum product pattern that we're working with. And in this case, because the number on the end is negative, we need opposite signs in our factors. So for example, we could use negative 2 times 2. Those multiply to negative 4. But negative 2 plus 2 is clearly 0. So this is a fail. That doesn't work. Well, how about negative 1 times 4? Negative 1 times 4 is also negative 4. But negative 1 plus 4 is positive 3, so that fails. There's only one other possibility. And notice we need a negative 3, and this is 3. So we're going to switch the signs of 1 and 4 so that we have a 1 times a negative 4. That product is also negative 4, and 1 plus a negative 4 is the desired result, the negative 3. So here are our factors, and that will allow us to factor x squared minus 3x minus 4. Again, x's are in the first positions when we start off a trinomial like this with an x squared. And then we put a plus 1. And then we put a minus 4 here to get the x minus 4. And here's our solution right here. In this next section, we're going to factor a quadratic trinomial that has a GCF. We're going to leave the parenthesis there, and we'll put in x squared in, we'll put in a minus 3x, and we'll put in a minus 4. And so we've gotten the GCF factored out of there. But before we stop, let's look at this. X squared minus 3x minus 4. Isn't that the trinomial we just factored? It certainly is. This can be factored further because there are factors of negative 4 that add up to negative 3. And if we were to go back to the previous page, we would see that we need x minus 4 times x plus 1. And I'll let you do that yourself if you want. You can rewind this video. So this is a GCF and the sum product technique. Sometimes I call this sum product technique reverse FOIL. In this next example, we're going to actually do it two ways. I'm first going to do it by factoring the GCF, and then I'm going to go over factoring by grouping, which is probably the most complicated method for factoring quadratic trinomials. So in our first try at this one, we recognize that 3x squared should come first, and 12x should come next, and then the minus 63. That puts it in standard form. Biggest exponent to the number. And now we're going to look for a GCF, and it's 3. 3 goes into 3, 3 goes into 12, 3 goes into 63, and we get 3 times x squared plus 4x minus 21. And now we ask, are there factors of negative 21 that add up to 4? And how about 7 times negative 4? 7 times negative 3. That's negative 21. And 7 minus 3 is 4. These factors work. So that means we can now factor the x squared plus 4x minus 21 into x is in first positions, plus 7, so x plus 7, x minus 3. And we are done factoring this quadratic trinomial. But let's take another look at this. So I'm going to write it down again. And I'm going to write it down in standard form as we did a moment ago. So it's 3x squared plus 12x minus 63. And this time we're not going to be clever and go, oh, I know I should always look for a GCF and factor it out. Let's pretend that we don't notice it. And let's see what happens. We're going to learn factoring by grouping, or FBG, now. This is also known as the AC split the B method. And where does the A and the C and the B come from? Well, the quadratic trinomial in standard form has this form. Some number A times x squared, some number B times x, and then some number C on the end. So if we're going to multiply A times C, it means we're going to multiply the 3 times the negative 63. So the AC is negative 189. And then the idea here is this, that we're going to determine factors of negative 189 that add up to the positive 12 in the middle there. 189 is a pretty good sized number. How are we going to figure out these factors? Well, let's start simple. Let's take 189, and I think 3 goes into this. 3 times 63. Now, if you don't believe that, let's just test it. 3 times 3 is 9, 3 times 6 is 18. It works. So 3 times 63. So we're building a tree structure, kind of like building the roots out. And now 63, we looked at that number a few minutes ago. That's 3 times 21. 21 is 3 times 7. So what we've done now is this. We've actually figured out what the 2 prime roots of 189 are. So the numbers are 3, which occurs 3 times, and then 7. So from these 4 numbers, we can construct the factors of 189. We'll worry about the sign of 189. In fact, it's got to be negative in a moment. So one factor would be to take the 3 and then multiply by 3 times 3 times 7. That's 9 times 7, which is 63. We knew that. Another possibility is 3 times 3, which is 9, and then 3 times 7, which is 21. Another possibility is 3 times 3 times 3, which is 27 times 7. So these are probably going to be useful to us. One of these will probably be the key, one of these sets of factors. So I'm just going to write down, without signs now, we can play with the signs in a moment, 3 times 63, 9 times 21, and 7 times 27. Now let's see if we can figure out which combination will give us a positive 12. Well, if 3 or 63, if either one were negative, we would get a number that's nowhere near 12. In fact, the number would be either plus or minus 60, which is nowhere close. And 21 minus 9, like say we had 21 and negative 9, that's 12. There it is. So the 7 and 27 won't work either. Okay, now why did we do all that? Because this is the AC split the B method. The whole idea is that we want to rewrite this 12x as the sum of 2x terms. So again, I'm going to write down the 3x squared plus 12x minus 63. And with our work up here, the negative 9 and the 21, we're going to split the 12x into negative 9x plus 21x. And we have our 3x squared, and we have our negative 63, like that. Now I think you can start to see why this method is a bit longer, but it illustrates the technique well. And I'm doing a little bit of extra writing because I'm teaching. So in this method, once we've split the b, and I'll say that that's what we did here, we want to factor these two groups. And we're going to use GCF factoring here. So 3x squared and 9x, 3x is the GCF of that. And 3x times x is 3x squared. 3x times minus 3 is negative 9x. Now there's a plus sign here, so we're going to put a plus sign here. And we look at 21x and we look at 63. 21 times 3 is 63, so the number 21 is the GCF of this second group. And 21 must multiply x to get 21x, and 21 must multiply minus 3 to get negative 63. We're almost done now at this point. We're going to assemble our answer as follows. The 3x and the 21 are added together, and then the x minus 3 is a repeating factor. And this is a factored form answer. So if we were to factor the GCF of 3 out of 3x and 21, we would get 3 times x plus 7 times x minus 3. The most simplified factored form, where 3 is a GCF. And if you recall a few minutes ago, we go back up to the top, that's exactly what we had done in our first take on this problem. We had pulled that GCF out, which was 3. So in this example, we're going to do the AC split the B method again, but there is no GCF. And the numbers are a little smaller, so this will probably be a bit quicker. So I'm going to speed it up this time. So AC comes from 2 times negative 5. That's a negative 10. We're looking for factors of negative 10 that add up to the B value, which is 9. And since this is negative and that's positive, we need the bigger factor to be positive and the smaller factor to be negative. 10 minus 1 is 9. So in other words, 10 plus a negative 1. And so these are the factors at work. And we will split the 9x into 2 pieces using those two numbers. And so when we do this, we get 2x squared plus 10x minus 1x minus 5. Now we'll do some grouping on the 2x squared plus 10x and on the negative x minus 5. And again, at this point, we look for GCFs. And in this first group, the GCF is 2x. 2x times x, 2x times 5. So 2x times x plus 5. Minus, and we're going to take this 1 right here, because it's a 1x. And then x plus 5. That's because negative 1 times a 5 would give us a negative 5. And now we can assemble our answer. And you can see this is going quite a bit quicker. Our answer is 2x minus 1 times the repeated factor x plus 5. We're going to test or check our answer by double distribution, also known as FOIL. So FOIL says that we multiply 2x times x, which is 2x squared. Outer terms, 5 times 2x is plus 10x. Inner terms, negative 1 times x. And last terms, negative 1 times 5. And clearly, the 10x minus 1x, that looks pretty familiar. There it is up above. And we combine those and we get 2x squared plus 9x minus 5. Check. We got back to the beginning. We're now going to look at factoring a perfect square trinomial. The pattern here is a squared plus 2ab plus b squared is equal to a plus b squared. So we need to recognize when we're looking for this pattern that the first part of our trinomial is a perfect square, and the last part is also a perfect square, and that the middle is twice the square of the first part times the square of the last part. As we can see, this will factor into a sum of two terms, quantity squared. So let's look at an example. We've got x squared plus 10x plus 25. Now, pretty quickly we see that x squared is x times x, so that's good. And the 5 times 5 is a 25, so that's good. In other words, what we're looking at is x squared plus 10x plus 5 squared. Now the question is that 10x equal to 2 times the x times the 5? Yes, it is. So this factors into x from here and 5 from here, and this is a positive 10x, so this is x plus 5 squared. 4x squared minus 24x plus 36. Well, 36 is 6 squared, but 4x squared? Oh wait, 4x squared is 2x squared, isn't it? Okay. But notice something else. This one also has a GCF. Let's just take that GCF out first, because taking the GCF always makes things easier. So we'll take a 4 out, and we'll get x squared minus 6x plus 9. And this is 4 times x squared minus 6x. And 9 is 3 squared, isn't it? So it looks like we've got our x times x. That's a perfect square. And then the 3 squared, clearly, that's 3 times 3. That's a perfect square. Question is this 6 product of 3 times x times 2? 2 times 3 times x is 6x, isn't it? Check, that works. So in this case, we've got our GCF 4, and the x times x, the x squared, that gives us an x here, and the 3 over here gives us a 3. Now this is a minus 6x, isn't it? So we need a minus 3 here in this case, and we're done. Let's just expand this one to make sure it actually worked. So x minus 3 squared is x minus 3 times x minus 3. So this is 4 times, let's see, x times x is x squared. Negative 3 times x is negative 3x. Negative 3 times x is negative 3x. And negative 3 times negative 3 is plus 9. When we combine these, we'll get 4 times x squared minus 6x plus 9. And finally, we can distribute, and we get 4x squared minus 24x plus 36. And we're back to the beginning, aren't we? So this worked. Last but not least is the difference of squares pattern. This is a fun factoring pattern. It's easier than the factoring by grouping. It's easier than perfect square trinomials. This time, the pattern is if we see a square minus a square, it breaks up into a plus b, a minus b. So a squared minus b squared is a plus b times a minus b. So if we see a square like z squared and we see 81, 81 is a perfect square, isn't it? It's 9 squared, which is a difference of squares. I like to call it DOS for short, difference of squares. It factors into z plus 3 times z minus 3. That's it. We're done. Now, why does this work so beautifully? Well, if we were to FOIL this, we would get z times z, which is z squared. We'd get negative 3 times z, which is negative 3z. The inner product would be positive 3z. The last terms would be negative 9. And notice what happens to those outer and inner products. They knock each other out, and we're left with just the product of the first terms minus the product of the last term, z squared minus 9. This always happens with difference of squares. The outer and inner products knock each other out. Finally, one last example. 9y squared can be seen as 3y quantity squared, and 49 is 7 squared. So by difference of squares, it's 3y plus 7 times 3y minus 7.